get ready to go. Last week we did linear regression, and you did some cool projects. Today we're gonna cover logistic regression, and we're gonna have a new fun project for you all to work on. So take it away, Naveed.
Yeah, for so we covered the regressions where the goal was to predict a continuous variable. Now, sometimes the output that we are do want to predict is not a continuous variable, and for majority of the time, it's mostly classifications. Regression studies, although they are there, but most of what I see is classification, even if it's just the outcome is directly you are predicting between two quantities, or if you are doing something advanced. So for instance, if you are doing let's say object detection, there as well you have certain predefined categories that you have to predict something for. And image segmentation as well, you either have to declare a pixel to be belonging to some object or a background. So most of what I see is classification in machine learning, and that's what we are going to cover today. The basic building block, the simplest algorithm that we have in order to do classification is called logistic regression. So let's build the case for why is logistic regression a good algorithm for it, and why we cannot make use of the existing linear regression algorithm in order to do that. Okay, I've written these things in advance because it then takes time, and the loss function for logistic regression is a bit complicated, so I forget about it, and I have it in advance here. Um, Anyways, so here what you see is called the hypothesis function of a logistic regression. So previously for linear regression, the hypothesis function was this thing. So in order to produce an output, you have to take the input, multiply it with the weights, and then add the bias term in order to produce an output. That was linear regression. Now, in order to do logistic regression, we take that output and then plug it inside this function, which is called the sigmoid function. The question is, why do we do that? Why can't we make use of the linear regression? So let's see why is this not a good idea. Um, so for instance, take this hypothetical example where we have two classes. So these circles, red circles here represent the first class, let's call it the zero class, and then these crosses represent here the second class. So let's give it the label of 1. And let's see what happens if we try to fit a linear regression model to it in order to do classification, in order to decide between if something belongs to this zeroth class or this one class. Take so just for instance, we would take the example of if we have, let's say, a tumor of some size, and the idea is if the tumor is smaller in size, it is a benign tumor, and if it grows in size, it becomes a malignant tumor. This is just for example. So on the x-axis, you can consider this to be the size of the tumor, and on the y-axis, these are the two possible outcomes. So it can either be benign tumor, in which case the output is 0, or it could be a malignant case, in which case the output is 1. This makes sense, right? I'm not confusing you.
Yeah, so we want to make a model that will detect if a tumor is malignant or benign based on how big it is.
Exactly. So what you see here, these red circles and crosses, this is just some historical data. So what it is showing is that if the tumor is lower in size, there's a greater chance that it's a benign tumor, it's not malignant. But if it grows in size, then it becomes a malignant tumor. And we want to take a linear regression, or in other words, a straight line, to fit to this data, because we want to model this data, and for the reason that in future we would like to have a model where we can just provided the size of the tumor, and it should be able to tell us if it's a malignant tumor or benign tumor. Now, as we are aware that linear regression line does not yield 0 or 1, it yields a continuous output. So it starts from 0 and can go up to any number based on what the input is. Um, so how can we convert this into a classification case where it has either to produce a 0 or a 1? What we can simply do is that we can put a threshold. So you can say that if the output is, let's say, greater than this quantity, which could be anything, for instance, it's zero point 0.5, let's say, we say that if the linear regression produces something that is greater than zero point 0.5, we would declare it as 1. And if it produces something that is lower than zero point 0.5, we would predict this to be 0. Um, I'm just putting zero point 0.5 here because I've written here 0 and 1, but it could be anything. You can pick this threshold to be anything for the reason that linear regression does not yield an output between 0 and 1. It could be between 0 and any positive number. But the idea is that you just simply pick a threshold above which you declare that it's a 1 and below which you declare it is a 0. So this can work, right? We can make use of linear regression in order to do this. Well, by just the look of it, it seems that can work, but the problem is there are certain problems regarding linear regression. First thing is it is producing something that is not between 0 and 1. It would be producing something that could be a lot greater than that, while we just need between 0 and 1. So that's one thing, but we can ignore that problem for a second. Second problem with such a model for using linear regression is a classification model is suppose this was the original letter that we had, these red circles, but now we introduce something like there's another example that is now introduced. This is another extra example whose size is, let's say, this much, and it's a malignant tumor, of course, because after a certain size, all the tumors are going to be malignant, for the simple reason that if the size of if a tumor of this size is malignant, increasing the size further would definitely mean that it's also a malignant tumor. So there's no point in changing your model if there are certain examples that appear on the far right. We should the model should stay the same. It should not affect the, the model itself. But the problem with linear regression is if you introduce this and you retrain this algorithm using linear regression, if you remember, the goal of linear regression was to reduce the square differences. And in this case, if this is the, let's say, the newer example, and that was the previous line, linear regression line that we had trained, the difference that the model would be producing from the true output would be this much. And remember that this difference gets squared, so it's even a huge it becomes even more bigger, and definitely such a bigger loss would affect this line if you retrain it. So the line would tend to be tilted towards this newer example because of this huge difference. And that's why if you retrain this linear regression algorithm once again, this green line is what you'll get. Um, and you can see that there's a significant difference between the blue line, which was earlier, and this green line, which is after retraining. Why? Because it is trying to reduce this error. Now we have this much error. While in order to do that, it's also increasing these errors as well. So previously, this was the error, but now for the green line, that error is increased, even though it should also be closer to these points. But the point is there was so much bigger of a difference that it introduced errors in these as well, and still it was like the overall error between that one and this one is smaller. So if you're confused about this discussion, just ignore it. But the point is, if you introduce points towards on the far right, the linear regression line tends to cover that because it is reducing the square differences. Now, what is the consequences of that for our strategy to use this as a classification model? Well, the consequences are that previously we picked this threshold to be this zero point 0.5, and as a result of that, anything that was lying on this side of the line, we declared them as benign tumors, and anything that was occurring on that side of the line, we declared them as malignant tumors. Now, picking the same threshold here, you can see that the 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 threshold that we have picked now cuts the line at this point. So anything that is occurring on this side of the line are now declared as benign tumors, and anything that are occurred on that side of the line are declared as malignant tumors. So the problem that you can see here is because of this extra introduction of this example on the far right, the threshold that we picked earlier is now classifying these 2 points incorrectly. They are declaring that these are benign tumors, even though these are malignant tumors. And and that's because we have introduced something that is way far more on the right side. And intuitively, we know that it should not be something that it should be doing because, just like I said, if something is of a certain size, anything greater than that size is definitely a malignant tumor. So it should not affect the model. But linear regression, as you can see, is getting affected by this outlier example that we have introduced. Does this make sense?
Yeah, makes sense.
Perfect. So So for this reason, we need to come up with a model which is not a straight line, but it is rather doing something that looks like this. Let me change the color. I have introduced a mess here, but I'll try to. Okay, so we need a model that looks like this, somewhat like this at least. So it is flat on the left side. It is flat on the right side as you increase the size, and it makes this jump as you as the tumor, the benign tumors start becoming malignant tumors with increasing size. So for this model, it doesn't really matter if you introduce an example here or even there. This flats out. So it would always be producing an output of 1 if you keep on increasing the size of the tumor, and it would always be producing the output of 0 if a tumor is of a very lower size, a smaller size as well. So we need a model of this sort, a curve of this sort, which fits this data and not a straight line, right?
Yeah,
Okay, so the question is how do
reminds me
we
a little bit of like a transistor or something like that.
transistor? Yeah, I think the threshold after which the current starts flowing.
Exactly.
Yeah, that analogy works somehow. But the question is, how do we go from this straight line to that curve? Well, we can make use of something called a sigmoid activation function or sigmoid function, which is a nonlinear function which looks like this. So you take the output, you plug it inside this negative exponent, and the output that it produces, it squashes the output between 0 and 1. So whatever the value of z is, this activation function or this function is going to produce either a 0 or a 1 or something in between, in which case it produces, let's say, a 0 in cases where z is negative. So if you take a computer and create a numpy array of some negative values and positive values, and then you plug them inside this function and then you plot them, you'd see that for the values of z which are larger negative values, this line asymptotes at 0. And for the values of z that are positive, as you increase them, it asymptotes at 1 here. And if you plug in exactly 0 for z, what happens? So if you plug in e to the 0, which is 1, 1 divided by 1 plus 1 is 1 divided by 2, which is 0.5. So for z equal to 0, it is producing exactly 0.5. Anything on the left side starts going towards 0. Anything on the right side starts going towards 1. That's exactly what we require. So we need a function which squashes the output of this between 0 and 1, because that's what we are required here. The tumor could be either a 0 or a 1. It still is producing something in between, so it's not like it's producing a 0 or a 1, but it will be something in between. But what we can do is then we can pick a threshold. So let's say you pick a threshold of 0.5. We say if anything that is lower than 0.5 is 0, anything that is greater than 0.5 is 1. And this threshold picking, it's manual, so you can change this. Normally you can plug this to be 0.5, but if it is something of higher, um, like if it's something very critical, you can even decrease this. So you can say, even if there's a chance of 0.3, I would like this to be 1. And if it is lower than that, I would like it to be 0. So this threshold picking is your own choice. Any questions so far?
Nope. No.
Okay, so the rest of the story then is just what we've been doing for the linear regression. Now we have this model, we have these parameters. So this is parameterized by this W and B. And we need to come up with a way to um, figure out the values for W and B. Well, initially, because we randomly initialize W and B, whatever this model is producing would be way off than what the true output is. And in order to compute that difference, we need our cost function or loss function. So for linear regression, the loss function was MSE. So in MSE, we just simply take the differences, square them, and then accumulate it across all the examples, and that's our cost function. Well, turns out if you the loss function, the MSE loss function, you cannot make use of it here. Question is, why can we not make use of it? Well, the answer is because we have introduced this nonlinearity here. And because of that nonlinearity, if you now try to plot the loss function, let me see if I have plotted. Yeah, here. So it turns out if you now plot the loss function J with against any of the parameters, so let's say this is W, the loss function now looks like this. While previously in the linear regression, if you remember, the loss function looked something like this. Now, can anyone tell me what is the problem with this red loss function, which is non-convex? Felix, any thoughts?
Not right now. No.
Okay, Nishant?
Nope, not sure.
Okay, so the problem with this
I can take
non-convex,
a guess.
you know that, you know it already.
Okay.
Yeah, so the problem with this red loss function is, you see here, we have a lot of what are called local minimas. So previously, for this convex um, loss function, we just had a single minimum point at this for this entire loss, just this one, and it was called global minimum. Global minimum means this is the lowest point. We don't have any local minima. Now, what is the problem with these local minimas? The problem with these is, suppose initially when you started, the random initialization for W was, let's say, this, and you begin at this point. Remember how we update the values of W's? We make use of gradient descent. And if you remember, the equations for gradient descent, W was updated like this, right? What this was doing is computing the derivative of the cost with respect to W. What was the derivative? It was nothing but the slope of the tangent line drawn at that point. Um, so making use of gradient descent, we gradually reduce the value for the loss function. Now what happens if you have these local minimas is that if you reach at this point and you compute the derivative at this point, it would be a perfectly horizontal line. The tangent line would be perfectly horizontal. What is the slope of a perfectly horizontal line? It is 0. So if it is 0 and you take that 0 and you plug it in here, this entire equation, this part becomes 0. So W is equal to W, meaning no updates in W. So once you reach at this point, the loss is no longer getting updated, for the simple reason that gradient here is 0 and you are stuck at this local minimum. So you can say that while looking at the loss function, you can say you can confuse yourself into thinking that this is lowest point because it's no longer getting updated. But if you plot it, you'll see that it's not the minimum point, it's a local minimum. The minimum point on this plot is, let's say, this one. That's where I should be reaching, not this, because that's global minimum. But the problem is, how do we do that if our loss function looks like this? And for this simple reason, we cannot make use of MSE loss function because it results in this non-convex loss. And it is because of the reason that we have introduced the sigmoid function, which is highly nonlinear. Question is, how do we mitigate this issue? Well, we can make use of a different loss function, which is called cross-entropy loss. The cross-entropy loss looks something like this. It looks scary, but you will see shortly that it's a very simple loss function. But if you plug in this loss function, you then effectively make your loss function from non-convex, you make it again a convex loss function. Now, if you ask me, why do plugging in a cross-entropy loss function converts it from non-convex to convex? The proof of that comes from a concept in probability and statistics. It's called maximum likelihood estimation. I haven't personally looked into the details of it. There's, I think, a long proof which shows if you have a sigmoid activation function and you use a cross-entropy loss, the non-convex cost function becomes convex. So, of course, you're not getting into those proofs, but it comes from probability and statistics. You can study it there by the name of maximum likelihood estimation. But let's take a look at this loss function. What is it doing? So if you carefully look at this loss function, there are two parts to it. This is the first part, and then there is the second part. Why do we have two parts? Well, it turns out that, let's see, these are the two parts that we have combined. So we make use of a term, of a loss term, this when the true output is 1, and this when the true output is 0. So let's take the first one, negative log of y hat. How is this accumulating the loss? What happens if my model is producing something which is different than what the true output is, which is 1? How would this accumulate the loss? So if you take a computer and plot a log function, so you take some amount, some array, and compute the log of it, and then invert that by negating it by putting a negative sign there, the resultant plot would look somewhat like this. And because our model is producing something only between 0 and 1, we are not taking a look at a range outside it. We are only interested in something which is between 0 and 1, for the simple reason that our y hat, which is the output of the model, would be producing something that could be either 0 or 1 or something in between. And if you take this array and plot negative log of that values, you see a plot that looks like this. I'm not confusing you people, right?
Nope.
Okay. So let's see. I said that if the true output is 1, we make use of this loss function, which looks like this. Let's see what happens if, so the true output is 1. What happens if my model is producing something closer to 0? You can clearly see if the model is producing something closer to 0, let's say this, while the true output is 1, this loss is going to be very high. So it produces something like this. The more you get closer and closer to 0, the more higher the loss appears. Because the true output is 1 and the model is producing something very close to 0, which is not something it should be doing. That's how it is computing that cost. Now, if the model is producing something closer to 1 and the true output is also 1, the loss is going to be very minimum. If it is producing perfectly 1, the loss is going to be exactly 0 for that example. That's how it is accumulating the loss. That is for when the true output is 1. What happens if the true output is 0? If the true output is 0, then we make use of this loss function. Turns out if you plot this, the resultant loss, the resultant plot looks like this. So if the true output is 0 and the model is producing something closer to 1, the loss is going to be very high because it will be way off than what the true output is. And if the model is producing something closer to 0 while the true output is also 0, the loss is going to be minimum. It is going to be closer and closer to 0. So we have these two parts which accumulates the loss function. We want to, so we cannot plug in, like we need to somehow put these two into a single equation to which we can call our loss function. It turns out this is the equation which would account for both of them. Now let's take a look what happens, like how is it combining these two different parts. So this yi here that you see, this is the true output, comes from the data. And this y hat here is the prediction of the model. This I here is just simply representing the ith example. So we are summing over all the examples. So m is the total number of examples in our data. So let's see what happens if the true output is 0. If the true output is 0, we would be plugging 0 here, right? Because this is the true output. So if you plug in 0 here, this whole term boils down to 0. And this is also the true output. If you plug in 0 here, 1 minus 0 is 1. 1 multiplied with this thing is log of 1 minus yi hat, which is exactly what this thing is, negative log of 1 minus y hat when the true output is 0. And when the true output is 1, so you plug in 1 here, this term appears, boils down to this, and 1 minus 1, so this term becomes 0. And if this becomes 0, this entire portion, this vanishes, which is what that first part was doing here when the true output was 1. So that's how we combine these two parts to make this entire loss function. We just simply sum it over all the examples and take the average of it by dividing it with m. This makes sense, right?
So let me just ask something, because it's something I was just thinking about as I was reading this graph. So if you have, if the true output were, say, 1, and the predicted output were 0, technically, right, your loss would be infinite for that point. Am I reading
Exactly.
the graph correctly?
Yep.
And I thought, how can it be that you could have an infinite loss? But then I realized that this S curve is not exactly flat, right?
This would be infinite, but the question is, would your model be producing perfect 0 or perfect 1?
Right.
It would not be producing that, right? It would be some small negative, some small number if it is on the 0 side. It's not going to be perfectly 0. In that case, it's true that the loss would be infinite, but it's not going to happen.
Because that blue in the loss curve, or in the sigmoid curve that you have, that blue line, the logistic curve, sorry, that blue line never fully touches the line.
So it asymptotes here, but it never reaches that exact
Right.
1 value or exact 0 value.
So it
Right.
can always be adjusted to be a bit closer.
So it can go closer and closer, but like you'd never see something that would be exactly a 1 or exactly a 0. It would be, for 1 it would be something like 0.99999. That's the maximum that it can reach. You won't see it perfect 1 in any case. Right? Any more questions? Are you with me? Because I can't see your faces.
Oh, no more question.
Okay. So
No more math.
yeah, so the last thing that I was about to say was that you now have the loss function, you have the model. The only thing that is left now is training this model. How do we train it? You saw that we make use of the same old gradient descent to do that. So in order to update the value for w, let's say you take the previous value of w and subtract from it alpha times the derivative of the loss function with respect to w. And for the second one, the bias term, you do the same. This is in case where you just have one feature. What happens if you have multiple features? So if you let's say if you have 5 features or 10 features, you just simply do the same operation, just differ the weight that you're looking into. So suppose you're updating the weight for the third feature. So W3 would then become W3 is equal to W3 minus alpha times the derivative of the loss function with respect to W3. If you do it for fourth feature, you just simply change that, and this, the rest of the story stays the same. So with that,
Basically, what you're saying is we can add multiple logistic functions for multiple input variables as much as we want.
the
Right?
function remains one, so we still make use of just the sigmoid
Oh,
activation function. Only the W's,
the Z function you can
the
add.
Z function that so Z is equal to, like, if we, let's say if we are looking into the cancer example,
Yeah.
let's say you are just looking into the size of the tumor, so that's just one feature. In that
Yeah.
case, size would be, let's say, X, so the Z would be Z equal to W times X plus B. Now suppose you also are looking into the texture of the tumor. In that case, Z would become Z equals to W1 times X1, which is the size, plus W2 times X2, which is the texture, plus B. So the Z changes, but then you check the same Z and plug it inside the sigmoid. So the sigmoid stays the same.
Make sense?
And with that, we can go towards coding.
Okay, cool. Who's ready to see some code?
I'm ready.
I'm so ready. So um, we are going to look at an example today, which is the same example that Naveed was just telling you about how to detect if a tumor or a image of cells is malignant or benign. And I am not medically trained in any way, so I'm just explaining how I interpret the data myself. So this is this is our course structure, and if you scroll down to logistic regression, have a mini project here, and actually maybe I can ask you, you all, like, what are some examples of what are some use cases where you might consider using classification of two different things?
Something I think about would be, you know how like Apple has under iPhones like Face ID, stuff
Mhm.
like that. Maybe you could use something
Oh
for that.
yeah. So in this case, so that's interesting because with a Face ID, you're really trying to classify millions or billions of different images. So that might be more of a Naveed, that might actually be more of a regression, right? Because you're trying to tell the difference between the detected face and the face you're expecting, right?
Can you repeat the question, please?
Well, face detection.
Mm-hmm. So the question is if a face detection is regression or classification.
Yeah.
Okay, so face detection, let's see. If you are doing it using the bounding box, so
Yeah.
you want to draw a bounding box around the face, it can be very well modeled as a regression problem, because what you would be predicting would be the coordinates of that bounding box. Now, the coordinates can, like if it's an image of, let's say, 1,000 by 1,000 pixels, uh, the coordinates would be the number of the particular pixels, where one corner lies and where the second corner lies, and so on. So this can be modeled as a regression problem.
Hmm.
But if you want to model it as a classification, I think you can do that, because pixel numbers are, you already know that all the images that you would be feeding would be of a certain fixed size, and let's say it's a 1,000 by 1,000 pixel image. You know that my x coordinate is also going to be one of the 1000 classes, and my y coordinate would also be one of the 1000 classes. So you can also do this using a classification as well. Both would work.
Yeah, how about some simpler examples where you could do classification? So like Sol had the example last week where you would have people's blood sugar. And that's just one variable, and then based off of that, they would detect if that person has diabetes. Or you could have multiple variables. You could have, the person's BMI, their blood sugar, their age, their weight.
Another example would be if there's an item where you would want to predict if this would get sold or not. So based on some features of it, you would want to see if someone would buy this or not. So it's a binary decision, either 0 or 1.
Yeah. With images, it gets more tricky because then you have to think, how does that image get turned into numbers? But it could be different ways. The example that we're going to use today is, I believe it is, actually, I'll just open up the notebook right here. So it's this breast cancer Wisconsin data set. And the way that they have collected this data is using a method called fine needle aspiration. But I think this helps me to understand what's going on in the data set. Basically, they've taken a needle, taken some tissue out of people's breasts, and then they've taken a bunch of microscopic photos of that tissue. And so in each photo, there is a whole number of cells in that photo. But each data set is one photograph, which means that you'll have different features like the average size and the maximum size of the cell. So that's just something that's kind of key to understand when going into this data set. And yeah, so this is really familiar to you. We will be using a new part of sklearn, and you can see the whole documentation for this up here, but it's going to be way easier to just show an example. So let's look at the data set that we are working with for this example. As I mentioned, you'll have stuff like the mean radius of all of the cells in that sample, the mean texture, perimeter, smoothness, so all these different things that can be quantified from the image. And then they'll have stuff like worst, which means the maximum. So really, it's just a bunch of things that have been measured out of that image. And then they do that for how many different images? Actually, I haven't. We'll see that in a second, actually. So here, we're doing a label encoding. And I think we've done that in the last... No, actually, we haven't done this yet, Naveed, with this group, right? A label encoder.
Yeah,
No?
we haven't done this because
Yeah.
previous one was regression.
Yeah. So the label encoder basically is just a really simple feature of sklearn, where you can take a column like this, which would have M and B, and then convert those into zeros and ones. And it will do that automatically based on how many classes there are. But we really need to have like numbers in order to train our model. And so here we want to have a quick idea of like how many malignant and benign detections there are. Because I think the way that they would have marked this is by having actual medical professionals go through and decide which ones are malignant and benign. So this would be, how many of each type of sample there are. So the next step would be to look through all of the different features and see if we see some kind of pattern between the diagnosis and the features. So we should have here a diagnosis. That's it. So the feature the diagnosis feature is called diagnosis ank, and we should see that here. Here it is at the very bottom. Let me zoom in a little bit. That helps. That doesn't really make it any bigger. So this diagnosis is either 0 or 1. And everything here are the other features that have been measured from the samples. So do you all see some kind of pattern or something that we could hold on to as something that would be useful? And just to look at the colors
Can
here.
you move the video to the left side?
Oh, sorry.
Yeah.
My fault.
No worries.
Yeah. So here we see, look at the color scheme we have. Goes 1 is white, and then minus 0.3 is black. Let's see if this helps it. Yeah. I could also do like this, which a little bit bigger.
And what are we looking at? The cells?
Yeah. So what we're
This
looking.
is describing the cells.
Yeah. So each item in this data set is one image that has a bunch of cells in it, and these columns here, those are what has been measured out of it, out of each image. So, and then this is the diagnosis, obviously. So we really care about this one row. We want to see which features are affecting the diagnosis. Does that make sense?
Right. Yeah. So I guess there's a bunch of features that are like above 0.7, right? So they are affecting quite a lot. I don't know what they mean though. It's like area worst,
Yeah.
radius worst,
Yeah. Yeah.
perimeter mean, so and so on.
Yeah. So let's look at those. So we have like radius mean, perimeter mean. Makes sense that those are similar because they're both size related. Area mean, same thing. Concave.
So this is the size of the cell, or do you know?
So yeah, this is the mean size of every. Going back to this image.
Yeah.
Each row in this data set is an image that has a bunch of cells in it.
Yeah. Yeah.
So this will be the mean size of every cell in this image.
Mm-hmm.
Yeah.
Okay. Yeah.
So yeah, we don't need to go through what every single one means, but we can definitely just pick one out that looks promising. If it has a high correlation, that might be something that's worth investigating. So for this, I just picked the radius mean. There might be one. Actually, perimeter worst is a bit better. Concave points mean is also a bit better, but for this example, I've just picked the radius. And let's have a look at the distribution of the different average radii for each sample. We see a lot that are between 10 and 15. We see some between around 18. So who knows? Maybe some of these higher ones are more likely to be malignant. We really have to look further in the data to see that. Here's a plot. Oops. Let me show that image fully so you can really see what's going on here. So here's a plot which shows the malignant ones on top, the benign ones on the bottom, and the average radius. So clearly what we can see is that bigger cells are more likely to be malignant, right? And you can imagine, you can imagine putting in a logistic curve here. What you can't see here is how many of these samples are on top of each other. So it could be that these are just a few outliers here that are overlapping. So you could probably make a better graph of that. But that's what I wanted to show this, just to show what we're trying to really fit a curve to. And the next thing that we do is probably quite familiar from the last exercise. We are just going to select which features that we want to use. And, as Naveed mentioned, we can use as many features as we want. So actually, I'm going to just remove the diagnosis and ID features, and then we'll train a model on all of the remaining features. So all of these features.
Okay, Jim, so in the X, we take all of the features, but if you go down in X2, we only pick the concave points first,
Oh, yeah.
and then we make use of that one.
Why did I do that?
So we wanted to see how would just one feature, which is mostly correlated, produce output, and then what happens if we try to use all of them. So X contains all the features, and X2 just contains the one.
Oh, yeah. So what we have here is, thanks for clarifying that. So here we have the first example. We've just taken one feature. And actually, we could do radius mean here as well. But in here, we've done all of the features, just to make that clear. So I've actually done both. We've actually done both ways. So if we run on just one feature, like concave points worst, and we get 0.5, let's see what happens if we do radius mean. It's about the same. That was the feature that we just looked at. And this should be really similar. This should be really familiar to the linear regression code. Actually, I don't really think there's anything different here aside from the logistic, aside from the class that you're importing.
Yep.
It's all the same. And yeah, as Naveed pointed out, you have to kind of look carefully. But here we're using X2, which is just one feature. And so this is the only difference here. If you just put in X2, you can get one feature. And here, if you put in X, you can train on all of the features. Does it make sense so far?
And for all the features, we then are also doing this standard scalar. So I talked about this last time.
Oh, yeah.
That if you're using multiple features, then you'd have to normalize them.
Right. So this code here is normalizing, as we discussed last week. It's normalizing by the mean and the standard deviation. So yeah, we had 85% accuracy for just one feature, but then for all the features, we had 99% accuracy.
Which just means...
Sorry, Naveed? It's kind of dark. So, can someone here explain to me? So that's accuracy. And can someone explain to me?
His electricity went out.
Oh, okay. Yeah.
Because his light was on before, and then everything is turned off.
That happens occasionally. But can...
Wow.
Yeah, go on.
Nothing.
It hasn't happened since we started this course. Here, let me remove them. So I hope that makes sense. I hope I sort of explained how to do the logistic regression. I think the main thing is to understand how to choose particular, as you guys learned last week, how to import the data, how to choose the features you want. do the scaling, and the rest of it is really the same. You definitely are making sure that for this model, the y data is zeros and ones, instead of just any value, and we do that by using the label encoder, which is just really simple, just replacing these m's and b's with zeros and ones. So
Yeah.
So
with this model, we can also decide to choose several features, like not just one, right? I think in the linear regression, we only chose one before.
Yeah, in the linear regression, what I actually did was I made 2 different notebooks. I just thought it made it a bit simpler. So you'd like single variable and multivariable.
Okay.
But these notebooks are so similar, as you can see here. Like the difference is really just what you pass into. Is really just what you pass into this this train, this fit function here. So yeah, they work. There's a little bit of weirdness when you just have one that you have to like reshape it into a size that the fit function is expecting, but I wouldn't think too hard about that. Cool. So you all think you can do that? No problem.
I think so. I'm just wondering, is there a way to, like, other than just trial and error, to find what features are best to predict the outcome? Because I'm wondering, like, there's the individual features, but then some of the features might overlap, like they have some overlap, so they're not actually improving the model as much, but then there might be some others that actually add some information and make it substantially more accurate.
Yeah, that's a really valid point. Like if you think about like radius, mean radius, and mean perimeter, like if you're already training on the mean radius, adding mean perimeter adds almost nothing. Well, it should add nothing, right? But adding something else like symmetry, you'd expect to be way more valuable. So yeah, for me, it's mainly trial and error. And I think you can see how fast it is to try different things here. Like this is a case where it's really easy. We could try. We could probably get really close to this 99% if we just pick a few really important features. Are there methods where you could sort of do that automatically, like automatically choose the best ones? Yeah, you could definitely write an algorithm that would do that trial and error for you. I haven't done that before, but I can imagine how that would work, right? You know what I mean?
Yeah, I mean, you could, like, there's probably a way to just have it automated, like it just tries all the different combinations and then chooses the best one.
Yeah,
but there's probably also a way to analyze the data and somehow choose more intelligently, but I wouldn't know how. Yeah.
So looking at this data,
right?
Well, one thing that for sure, so one thing that you can also see from this crazy heat map is that if we look at something like radius, if we got something like perimeter mean, and I know this graph is so large, it's kind of hard to deal with. But if we look at something like radius mean and perimeter mean, those
are
two
the same, basically.
are 100% correlated, right?
Yeah.
So we already know that it's completely redundant. And
Yeah.
there's some others which will also be very closely correlated. So that's a good point. Where it's like, if we really want to minimize the amount of features that we're using, then we could definitely look at this correlation matrix and do that. Good, yeah, interesting train of thought. One of the reasons why this is different than doing it with like deep learning models is like once we're training with deep learning models, there really is a lot of trial and error involved, because it takes time to train the model, and there's just so many different features and hyperparameters that you can change, that normally there's a human involved in the trial and error process, because it's expensive to try everything. But in this case, it's very cheap.
Okay. So can you show the outcome? Like so we have this 99%
Yeah.
accuracy. Is there any graph as well that like we can see
Mm.
where it draws the line or something like that, like similar to the linear regression?
Yeah, we could draw that. I think what we will see, yeah. Let's have a look if we can get the model parameters. So what we could do is we could take these coefficients, and the reason why we have all of these coefficients is because we have because this is trained on many features, and we could draw that. Now for this first one, which is just trained on one feature, you're going to get a similar graph to what Naveed showed before. Now this one, it can't actually be visualized in 2 dimensions. You can imagine with one feature you have a line, with 2 features you actually have a surface now.
Yeah.
And then with 3 features it just cannot be visualized correctly. But that's something that we could do. Maybe if we have, I guess we're pretty much out of time.
Yeah.
That's a good suggestion to add in there, like we had in the other notebook. I just want to go quickly through the idea of accuracy a little bit deeper into that. If you have a couple minutes, can someone explain like how is accuracy calculated for something like this? Like, what does this 99% mean?
I guess like let's say out of 100 times, like how many are like the prediction matches the actual.
Exactly.
Yeah.
Exactly. And so if you are detecting, let's say, cancer or COVID, why would accuracy not always be the best way to measure how good your model is?
I think I know what you mean. Maybe because like even with the testing, it's not 100% accurate. Like for example, if you do a COVID test, it might show negative, but it just didn't really accurately catch the infection or something like that.
Yeah. So if 99% of people don't have COVID and 1% do, if our model just says it just always says you don't have COVID, that's already 99% accurate.
Okay.
So that's due to this difference between how many are malignant, how many are benign. We actually really want to catch the the ones that are positive. So that's where we kind of get into this idea of true negatives true positives, false negatives, and false positives. Do those make sense? Those ideas?
Yeah.
Yeah. So, Nishant, can you just explain what are these four things mean?
Basically, the true negative is like actually, I'm not really sure what true negative and true positive mean, but
Yeah.
I think false positive and false negative is basically when it's supposed to be correct.
Mhm.
False positive is when it's correct, but it's actually supposed to be wrong. But false negative is when it's wrong, but supposed to be correct.
Yeah. So it kind of depends on how you define your labels. But let's say our model is trying to detect cancer, right? You could also say your model is trying to detect a healthy person. So then that would just flip everything. But let's say we're trying to detect cancer, then a true positive would mean they had cancer and our model detected it. A false positive would mean they didn't have cancer, but our model said they did. A false negative would be they did have cancer, but our model said they didn't. And then a true negative would be they didn't, and the model said they did. So you, depending on what you're trying to do, understanding all of these is important. And so this is often visualized. This is not visualized here, but it's normally visualized in a prettier way as what's called a confusion matrix. So like knowing all of these values is really useful. Knowing that, okay, our model had no false negatives, but it had one false positive when we tested it. That's interesting. And accuracy, as Felix described it originally, is all of the true positives and the true negatives. So whatever was correct out of everything, out of all of the predictions. And then there's a couple of related, things where you just take, precision. So like when the person had cancer, how often did the model predict that correctly? So completely ignoring all of the people that were healthy. Completely ignoring all of the negative diagnoses. And then recall is when the person did have cancer, how often did the model correct it? So completely ignoring all of the healthy people. And those are just and then there's something called an F1 score, which is just a combination of all of these. But the main point here is that basically it's not just accuracy, depending on what you're looking at. Because if it's not just accuracy, because then a model that always predicted everyone was healthy would be 99% correct. It's really a matter of understanding all of these values here, if that makes any sense. Cool. So we have another mini project coming up, which we're going to go over on Tuesday. And this one is really fun. So basically, the idea of the project is that you're going to have a data set. So it's here under Logistic Regression mini project. And if you want to use your own data set, that's also fine. But the data set that we've chosen for this is called Machine Learning from Disaster. And the goal is that you get a CSV. It's a little bit messy, so don't worry too much about how you clean it up. If you want to delete rows, delete columns, that's fine. And yeah, if you are struggling with something there, just write in the chat. But the goal of this is, given a list of people that were on the Titanic, their names, their ages, their sex, their cabin number, you got to come up with a model that sorts them into two groups: who's going to live and who's not going to live. And then we go over that on Tuesday, and we see who gets the best results.
Is this based on real, like, data?
This is real life. Yeah, there's
Okay.
people's lives in your hands right now.
Okay, sounds fun.
Yeah, it's really cool. So you have this logistic regression notebook that I just showed you that we just went through, and yeah, it would be great if you could figure out how to take this data and run it through a logistic regression. It shouldn't be too difficult since all the code is already there. Make sense?
Yep.
All right.
Cool.
Yeah, cool. Yeah, thanks a lot. And after this, we're going to be going over the next topic is going to be neural networks after this. So pretty excited about that.
Thanks, James.
Yeah, thanks a lot, and talk to you on the chat.
Yeah.
Yep.
All right, see ya.